session is one of our planetary mission concept studies. So Rob, you have 10 minutes.
Okay, thanks. So I'm going to talk about a planetary mission concept study I've been working on for the last few months. It's called MOSAIC. It stands for Mars Orbiters for Surface Atmosphere Ionosphere Connections. I'm just a figurehead for a big effort involving about 50 scientists from across the US and Europe, including 3 people who you'll hear from just after me. That's Luca Montabone, Scott Guzevich, and Leslie Tampari. Plus a great team of dedicated engineers and mission designers, et cetera, at JPL who are fleshing this concept out, including Nathan Barba, who will be speaking in the session after this.
Rob, are you still there? I'm not hearing you.
Sorry, can you hear me now?
Yes.
Hello. Yeah, next slide, thanks. Okay, yeah. So different parts of the Martian climate system have either been largely unexplored, like winds and things like shallow subsurface ice, or explored in very narrow regimes like at fixed local time. So we don't have a good idea of how the Martian atmosphere behaves globally and diurnally, how the different parts of the climate system talk to each other. In addition, we don't really understand the connections between the lower and upper atmospheres. Some recent work, for example, by Nick Heavens and Mike Chaffin have shown that dust in the lower atmosphere can boost hydrogen escape by factors of up to 20, with the physical mechanism not well understood. So the MOSAIC concept is all about connections between these different parts of the climate system and observing them simultaneously in order to provide the observational basis for understanding the climate system as a whole. So just this chart here shows the goals and the objectives of the MOSAIC study. If you just press next 3 different times. Starting at the bottom here, the idea is to characterize the volatile cycling between the subsurface, surface, and atmospheric reservoirs, then to characterize the structure and dynamics of the lower middle atmosphere on both mesoscales and global scales and how it varies geographically, diurnally, and across seasons. Then to understand how variability in the thermosphere and ionosphere and the escape-based atmosphere correlate to conditions both in the lower middle atmosphere and in the space weather environment, and then to characterize the field and plasma flows both in the upstream solar wind and throughout the entire Martian ionosphere and upper ionosphere to separate the spatial from temporal variabilities. Okay, next slide. Okay, so the MOSAIC concept, in order to address these 5 mission objectives, has 8 different investigations, and their titles are shown there if you can sort of turn your eyes sideways. And different combinations of these investigations can address these different objectives by observing the relevant quantities simultaneously. This is the ice distribution, the structure of the atmosphere, the diurnal behavior of the atmosphere, which is underexplored, as I mentioned, the thermosphere, the ionosphere, the exosphere, and the neutral escape that happens there, then plasma and ion escape in the magnetosphere, and then the space weather environment, which affects it. Okay, next slide. Okay, so there's a lot of text here, but the important point is that these 8 different investigations, each given their own color here, so each investigation involves measuring the relevant quantities there. That's the ice in the subsurface, the geographic and altitude distribution, things like pressure, wind, aerosol concentrations, water vapor, ozone in lower middle atmosphere. Investigation 3 is the complete diurnal and geographic behavior of the atmosphere from a synoptic perspective. 4 is the Martian thermosphere, including winds and composition. 5 is the ionosphere. 6 is the exosphere. As I said, 7 is the magnetosphere and all the plasma and fields there, and 8 is the solar wind. And each of these investigations are achieved by having observations from 4 different platforms, and different combinations of investigations are addressed by each of the platforms. The next slide, please. I'll talk about what the platforms are and the overall architecture of the Mosaic concept. The idea is to have a large mothership with the heaviest instruments on it in a fixed local time, low, sun-synchronous circular orbit, then to have three more polar orbiting small sats in complementary local times, then to have 4 different aerostationary spacecraft, one with a larger instrument complement and 3 with smaller instrument complements to be able to see all sides of Mars, and then to have elliptical orbiting small sats to make plasma observations. Okay, next slide. I'm going to go through each of the platforms separately. So the mothership platform, this is a big one here. The idea here is to measure the vertical profiles at a fixed local time of the ice in the subsurface and on the surface as well. In the lower middle atmosphere, this is temperature, pressure, water, aerosols, and wind. Wind is underlined because that is a new measurement that hasn't really been made before. It's been made on the surface, but not throughout the atmospheric column. And also the upper atmosphere to measure the neutral composition and density, the density of the ions, and also neutral winds, which also have never measured before. And shown on the lower left is the spacecraft. It's a large Class B spacecraft. That enormous antenna you see is the radar. This is a P-band synthetic aperture radar. The instruments are shown there in the lower right. I don't really have time to go through all of them. But you will undoubtedly recognize those instruments if you've been involved in the Mars atmosphere field. And as you can see, it's a large instrument complement. It's almost 300 kilos, so this is going to be about a 2,000 kilogram spacecraft. Okay, jump to the next slide now. Okay, so complementary in terms of, complementary in terms of the local time coverage. Go back again. It should say polar orbiting. Okay, thanks. Complementary to the mothership in terms of their local time coverage are going to be 3 polar orbiting small sats, each with a low mass instrument complement to measure vertical profiles of pressure, temperature, water vapor, aerosols, ice, and also through the radio occultations, the plasma density of the ionosphere. These will be in similar orbits to the mothership, but spaced out in local time. The idea is that the mothership would drop these off, and then each of these would move over the course of months into the position shown in the upper right. And so this will give us 8 different local times every 2 hours. Next slide. Okay, so these are the elliptical orbit small sats. These are to measure the Mars plasma environment, particular ion and sputtering escape, the magnetic morphology, and also topology, i.e. the connectedness of magnetic field lines, thermal plasma, and also a new measurement never made at Mars before would be the electric fields, which are important because they often help to accelerate plasma away from Mars and therefore contribute to atmospheric escape, and also neutral and temperature and pressure via the radio occultations mentioned earlier. These would be 2 spacecraft in a pearls on a string configuration to allow us to separate spatial and temporal variability. In elliptical orbits, there'll be spinners that's necessary to measure electric fields. They'll be dropped off by the mothership and then move into this elliptical orbit. There's also a smaller, cheaper, non-spinning version without electric fields because those are the big hog in terms of mass there. And the instruments are then shown there on the right again. Probably you've seen those before.
Rob, you've got another couple minutes.
Okay, sure. Next one. Okay, these are the last piece is the aerostationary spacecraft. The idea here is to actually go to the next slide or press next one. Next. Could you hit the next slide, please? There we go. Okay, yes. The idea is to measure a synoptic view of the lower atmosphere with the three instruments shown there to get a view such as shown here on the lower left, and Luke will talk about this next slide. Then also to measure the neutral and oxygen, neutral oxygen and hydrogen exosphere and escape rates using the instrument shown there. Next slide. And then also measure the upstream space weather environment that contributes to atmospheric escape and changing the effects on the upper atmosphere. Okay, next slide. There's also a descoped option for the mothership. As you can imagine, this is a very large and very expensive concept, but we're looking for a version of it that basically measures everything except the ice and the wind. This is much lighter payload and therefore significantly cheaper, but it preserves the constellation aspect. This would likely fit with the New Frontiers cost cap, so we're looking at this too. Okay, next slide. Okay, this is a movie here of how all the different pieces of the constellation can observe Mars simultaneously, where we have the aerostationaries seeing the whole planet, then we have the polar and elliptical orbiting elements also doing it too. So all these simultaneous measurements at the same time are necessary to build up the picture that we'd like to build up to really understand the connections between the different parts of the Martian climate system. Okay, next slide. Okay, lastly, don't want to concentrate on this too much because this is a science discussion here, but also there are exploration objectives. These same measurements will enable us to characterize things like the water ice resources. It'll allow us to characterize the atmospheric, the lower atmospheric state sufficiently to enable accurate weather forecasting, and things like ionospheric disturbances, which will help with communication and also demonstrate some important communication technologies. Okay, next slide.
Are you wrapping up soon, Rob?
Yep, this is the last slide. Yep. Okay, so just again, the idea is that Mosaic will unveil the complete Mars climate system from both mesoscale to planetary scales and from subsurface to the exosphere, while also enabling important pieces of what we'll need for human exploration. So it's because we need to understand these connections. They're currently poorly understood, and because our explorers will need resources. Between 5 and 10 satellites making these simultaneous measurements, and then for the first time after 2028 likely. It'll be very expensive, but there's options between $1 and $3 billion, and maybe we're crazy. So thank you, and I will take questions.
All right, well, actually hold questions. Put them in the chat window if anyone has them. We'll throw them in the discussion period.
Sounds good.
Let's pull up the white paper talks. So the first one is by Luca Montabone.
Can you hear me?
Yes, you can.
Good. Okay, so hi. I'm presenting a white paper idea to discuss the benefits and the applications for the geostationary orbit, which is a vintage orbit to observe Mars. What is an geostationary orbit? For those who didn't listen to Rob's talk, it is a planet-synchronous, circular, and equatorial orbit. It has an altitude of about 17,000 kilometers, and it's basically equivalent to a geostationary orbit for the Earth. We know geostationary satellites had and still have a great impact for Earth, and we expect that the same great impact happens for Mars if we use an aerostationary or satellites in aerostationary orbits. So what are the objectives of the white paper? First, to discuss the overall benefits of this type of orbit with respect to other orbits that have been used so far for mapping Martian surface, for example. These benefits can be summarized as continuous and simultaneous coverage of the observed region. This is a high priority for Goal 4 of the new MIPA goal document, so it's important to highlight that. we will look at future scientific and operational applications of this orbit, of satellites put in this orbit, particularly for atmospheric weather monitoring and possibly enabling weather forecasting. We heard from Rob, space weather is another application. Certainly, we can look at properties on the surface like thermal inertia and albedo. And as a future application, telecommunication and computational resources for future explorations are an important reason why we want this kind of orbit in the future. We will consider single satellites as well as constellations. You saw a movie from Rob. Right, just to wrap up, we have 20 contributors, welcoming many more. Please contact me if you want to be contributors or endorser. Thank you very much.
Perfect, thank you. Scott Guzevich, you're up, number 14.
Yep, I'm here. Just wait for the slide. There it is. So our white paper is titled Measuring Mars Atmospheric Winds from Orbit. And as you can tell from the title, our goal is to advocate for global atmospheric wind observations from orbit, and particularly following MEPAG goal updates and recent studies like ICESAG and NEMO. We're looking for vector-resolved horizontal winds, so we want the north-south component and the east-west component of the winds from the surface up to 60 kilometers or higher altitude, with a horizontal resolution of less than or equal to 300 kilometers. What the white paper will do is, beyond advocating for this, is to demonstrate and review the science case for measuring these winds. The new MEPAG goals document update that Don presented this morning highlights three goals or three investigations where wind is measured as a high priority science. It's both in Goal 2 and in Goal 4. This is, we believe winds are important, not just for atmospheric and climate science, but also for aeolian science and for geology. Wind has been one of the dominant forces shaping the landscape on Mars for 3 billion years or more. It's important for understanding how things like water and dust and trace gases circulate through the atmosphere between reservoirs and interact with the surface. And so really understanding how the Mars atmosphere and the climate circulates, and even looking backwards in time, we need to know how the modern atmosphere works. And winds are really the big key gap in understanding that. We're going to discuss the relevance of these measurements to future human and robotic exploration, both relevance to Mars sample return, launching a rocket from the surface of Mars, or landing a human-rated payload on the surface. Wind seems like something you would certainly want to know, and Goal 4 updates certainly discuss that as well. And then we want to mention that these measurements could be made now. We have instruments that are in development at Goddard, at JPL, at Ames, and other institutions that are ready for flight or very nearly so ready for flight. And we're going to review those instruments and discuss that these instruments could fly on the next orbiter that goes to Mars and make these key measurements. We're very interested to have additional co-authors or co-signers, and please contact me, and we're going to start writing soon. Thank you.
Excellent, thank you. Leslie Tempari is up next. She's number 15.
Hello, everyone. Okay, I'm Leslie Tempari from JPL. Our white paper concept is based on our mission concept proposal, which was not selected for study, but we believe that it's a really unique and highly valuable idea that would achieve both needed and very synergistic science. So it's entitled the Terrestrial Planets Comparative Climatology Mission Concept, and it would study the atmospheres of both Venus and Mars. And we would do that either with one spacecraft using solar electric propulsion that would go to both planets, or possibly trade that against twin spacecraft, one going to each planet. The idea here, the theme we have is to follow the water. Follow the water. That's because I'm a Mars person, but follow the energy, because the energy from the sun is driving the atmospheric circulation, and we want to understand some of the big picture outstanding needs, outstanding issues. So understanding broadly the differences in the evolution of the planet is what our goal is. We want to understand the evolution of these terrestrial planets in our solar system for their own sake, as well as a baseline for exoplanetary systems. You can see that we have some of our science noted here. We have much more in our one-pager and also in our draft white paper. You can see my point of contact information, our current co-authors, and then for more information, if you're interested in helping us or interested in endorsing this concept, then please see the one-pager at the link below. And that has the link to sign up. Within the one-pager, it has the link to sign up for helping us out. Thank you.
Thank you, Leslie. Colin Dundas is up next, number 16.
Okay, I'll just wait for the slide to come up. So this planned white paper summarizes active surface processes on Mars, which have really become a critical topic over the last 10 years. So at the time of the last decadal, we had relatively few observations of surface changes, but we've now seen numerous RSL sites, hundreds of flows and gullies, over 1,000 new impact craters. We've seen rockfalls and slope streaks and planet-wide sand transport. We've seen all sorts of effects of seasonal defrosting, North Polar avalanches, and growing Swiss cheese pits at the South Pole. And we expect other processes to be occurring as well. Many of the processes driving these changes have been surprising and uniquely Martian, and they're often still not well understood. So studying active processes is an important piece of comparative planetology, and it should also have lessons for other worlds. And I think there's a couple of other white papers that will talk about that aspect a bit. This white paper is going to show that we need to learn about these processes if we want to understand the current surface, let alone interpret recent climate variations or try to read the ancient rock record. And to give a couple of examples there are still debates over whether various slope processes indicate liquid water, such as whether gullies are created by modern processes or they're due to past snowmelt in a different climate. And it will also, for instance, be difficult to interpret ancient sandstones or other sediments if we don't understand modern sediment transport, which includes some processes that really don't occur on Earth. So this white paper is going to summarize what we currently know about surface activity, describe the open questions regarding it, and explain the need to understand it to address topics throughout Mars science. And we've begun drafting text. Additional contributors or signatories would be welcome, so please contact me if you're interested.
Excellent. Thank you, Colin. Claire Newman is next, number 17.
Thanks. So Martian dust storms are the biggest source of Mars climate variability, but to date, no Mars atmospheric model can spontaneously generate dust storms at realistic times and locations. Instead, most models impose the effects of storms based on observations in order to simulate the climate during one. So the problem here is that means we have no predictive capability. We can't simulate a climatology of realistic dust storms, let alone predict a specific storm in advance. And of course, if we can't do this for the present, that casts doubt on predictions of the past. So past dust cycles are crucial to interpreting geologic features such as polar layer terrain, but dust not only impacts radiative heating, but it also has many feedbacks with the water cycle. And so dust storms also, and dust storms hugely affect atmospheric escape as well. So there's also the very real possibility that if we're getting the dust wrong, we're also getting the climate and escape rates wrong for a wide range of past epochs. From a Mars exploration perspective, better understanding and prediction of major dust storms is going to be important to the success of future robotic and human missions, as they affect everything from air density, which affects aerobraking, to winds, which affects EDL, to surface, robotic, and human operations, including human health. So this white paper will talk about all of those impacts, and then we'll focus on how we can improve the situation. One big knowledge gap is when, where, and why dust is lifted. So to address that, we desperately need simultaneous environmental, meteorological, and aeolian measurements at the surface, as well as global and seasonal mapping of where the dust is even available across the planet for lifting. And another big unknown is what mechanisms are responsible for storm growth and decay. So to address this, we need a combination of improved models and detailed observations of the atmospheric dust distribution and climate response during storms, including time of day variations. So we have over 30 co-authors so far, and we are starting to write, but more are always welcome, and especially people who bring more of a geology, astrobiology, or human exploration perspective. So for more, please see our one-pager at the NEPAG site. Thanks.
Thank you, Claire. think I'm next one up. All right, I'm Serena Diniega, and in addition to helping with meetings like this, I also do science. So one of the areas that I do science in is looking at present-day activity on Mars and landforms in particular. And something that really struck me when the first images of Pluto were coming out from New Horizons was I started doing comparative planetology in my head with the features, but with Mars, not with the Earth. And I realized that we really were in a place in regards to Mars science that you could really use Mars as a baseline for understanding processes, and especially ones that are not, you don't find them on Earth. So for instance, sublimation-driven activity, or having a low-density atmosphere, or low gravity. That's the purpose of this white paper, is to establish Mars as a natural laboratory for studying surface activity on a range of planetary bodies. My personal bias is toward aeolian and frost-driven activity because that's what I've been working on. And so I give some examples here on this chart and describe them in the one-pager that's on the website. But I am open to potentially broadening that out. If there are other ways in which Mars can be used as a natural laboratory, for instance, we don't have to focus on just surfaces. I would like to focus on processes because I think that's one of the real advantages of using Mars as the baseline, is that it's presently active and we can be watching that activity, which gives us, a way to really understand the mechanisms and the controlling factors that we perhaps cannot do any other way. So I welcome inputs and contributions, ideas of other ways to broaden out this white paper, and you can contact me at that email address that's listed. All right, next slide, please. Okay, the other white paper that I'm working on is really focused on in situ measurements, focused on meteorological and aeolian, so wind-driven investigations. In numerous studies, the lack of knowledge about the winds and about the near-surface water vapor have come up as being key knowledge gaps that without knowing that information, we have a very hard time with calibrating our models and really understanding some of the processes. And a lot of this comes down to surface-atmosphere exchange. So that's what I'm focused on generally with this, is understanding how volatiles and sediment are exchanging between the surface and the atmosphere. And there's only so far you can get with models, and there's only so far you can get with kind of lower resolution global context measurements. I really think we're at a state where a critical gap are getting in situ measurements of these materials as they're moving off the surface and exchanging between the surface and the atmosphere. So the purpose of this white paper is to really look at how direct observations of these processes and exchange rates would fill the critical gap. So it's identifying what are the big Mars and planetary science questions that we really have difficulty answering presently without knowing more about those processes. So some examples shown here. Top right, you have a dust devil. There are lots of questions, as Claire talked about, having to do with the dust cycle and how dust is getting off the surface. So really seeing some of those processes and monitoring the dust fluxes over a season or over a Mars year, I think could really advance our understanding in that area. And then bottom right, you have a picture of Gale Crater. There's a lot of studies of the history of that crater and how its stratigraphy was formed, but also how its stratigraphy was exposed. So that's a huge amount of aeolian erosion that had to occur over a short time period. So anyway, it'll be getting into terrestrial instruments and maybe some mission concept ideas, but we're focused on the science questions. So again, welcome contributors. Thanks. Okay. The next person up is Tim Titus, number 20.
Hello, can I be heard?
Yes, go ahead.
All right. So alien processes are observed across the range of the solar system, from Venus all the way out to Pluto. And any planet that's rocky or icy, that has an atmosphere, even a transient atmosphere, is going to probably have alien processes. Mars provides a unique, as Serena said, laboratory to look at these features. We see a range of features going from wind streaks to ripples to dunes to yardangs, all exhibiting a range of timescales. And these is a record of atmospheric surface interactions that can benefit both climate, in other words, wind speeds, directions, over a range of these timescales, but also geology, the original source for the sediment, the alteration that occurred either in transport to the dune field or the ripple, and also in situ alteration. Mars, once again, is unique in terms of the solar system as we have so much data, continuous observations over more than 2 decades, both orbital and robotic. And so we have an image here of Bagnall Dune Field in the forefield. Curiosity touched that dune field, took measurements, and so voila, a new analog site for the solar system. Mars is also, I believe, a test bed for technologies. The Mars 2020 helicopter, I think, is a really good example, providing better resolution than you can get from orbit, but a longer range than you can achieve with rovers, possibly meaning that in a single mission we can look at multiple dune fields for comparison. So the desired end state for this white paper or white papers going into the Decatur survey really is a goals document or technology exploration roadmap for planetary aeolian processes. And we'll be talking more about this at the International Planetary Dunes Workshop next month. While we're not having the physical meeting, we are having a virtual one that will focus on white paper development. So thank you.
Perfect, Tim. Thank you. The next one up is Devin Burr, number 21.
Thank you, Serena and Tim, for leading in so nicely to the discussion I'd like to have here briefly. What I'd like to talk about is the importance of experimental facilities for Mars aeolian research. This is definitely a comparative planetology type white paper that we've developed. Aspects of it have been submitted to VEXAG and OPAG. What I'd like to talk about here is the Mars relevant aspects, but I will start with the text immediately below the title block, which shows how results from planetary aeolian experimental facilities have been relevant to Venus, Earth, Mars, Comet, and Titan. And this just agrees with what both Tim and Serena just said, that aeolian processes occur across the solar system, and we have the capability to understand those processes through experimental research. At the upper left of the slide is a downward-looking view of the Planetary Aeolian Lab at NASA Ames Research Center. At the very upper left is a vortex generator that doesn't exist there anymore. Then there's a low atmospheric pressure wind tunnel called the Mars Surface Wind Tunnel, and then below that is the Venus and now the Titan Wind Tunnel. In the middle of the slide is some text summarizing, drastically summarizing the review of the Planetary Aeolian Lab from several years ago. There were numerous strengths, including the greater accessibility to these facilities under the current PI. I'd like to point out the guidebook for proposers at the lower left of this slide. So thanks to Dave Williams for adding that accessibility. There were also some weaknesses noted, and then there were some findings that suggested things like having user workshops, including more subject matter experts in the management of PAL, including a research scientist or scientists with active interest in PAL. So these things don't exist right now, and they're things that might improve the utility and accessibility of PAL. I'd like to say that there is a larger user base now than there was half a dozen years ago, and that's terrific. There's people online right now who are conducting experiments in the Mars Surface Wind Tunnel, and I'm really excited to see their findings. The draft white paper that we have in development, that we developed about a year ago, thank you, lists a few different recommendations, and we'd love to have continued input on those lines, especially engineering input. At the very bottom of the slide, there are a couple of different wind tunnels around the world, in Canada and in Denmark, that I think could, that indicate some of the capabilities that we might bring to planetary wind tunnels. Thank you.
Thank you. We're now going to switch tracks a bit and focus on more climate records and polar science, or ice science. Isaac Smith is the first up, number 22.
Thanks, Serena. Thanks, everyone. In light of the announcement that the Decadal Survey is considering organization of processes across the solar system instead of individual planetary bodies, it seems that placing Mars in context of the solar system is a good idea. And Mars polar science with atmosphere and ice interactions is one of the stronger arguments for comparative planetology in the solar system. Mars is unique in the inner solar system because it has two volatile cycles that affect surface processes and record climate. Whereas Earth can be a good analog for Mars, it cannot serve in that role for the outer solar system because liquid state processes are rare, especially at the surface. Solid, gas, solid physical transitions dominate on Mars as they do in the outer planets. Importantly, Triton and Pluto are known to have layered ice deposits and active surface processes associated with seasonal and climatic changes. Thus, until we can send dedicated missions to study these processes, Mars, with its proximity to Earth and upcoming missions, will serve as an excellent analog. Additionally, Mars can serve as a test bed for applications and instruments where we can do cold tech, such as drills and other things to work in cold environments that will apply to places that we visit in the future, like Europa. So the slide, I've got several processes. There's way too many processes that are analogs to show on a single slide. But we have seasonal and permanent layered deposits, long-term residual caps, alien geomorphology, as we've heard a couple people talk about recently, and then seasonal processes. So there's some outstanding questions. The extent and quantities of solid volatiles on each planetary body, processes that act on those solid state volatiles, interactions between the gaseous phase and the surface, including geomorphology and atmospheric science, and then the climate record. So this is a white paper that I'd like to invite other co-authors and also any signatories. And if you want to talk about it more, please use my contact on the screen, and then there's the flyer down at the bottom. Thanks very much.
Excellent. Next up is Anna Grau-Golorfe, number 23.
Hello all. I'm just a point of contact for my team here. This is a team effort, and the list of authors and co-authors is in the PDF. The purpose of this white paper is to bring attention to the need of a better characterization and interpretation of the glacial and periglacial records of Mars, which are essentially those landforms related to the presence and motion and flow of ice. If we look at the box to the left, this shows examples of these features, which are concentrated in mid-latitude, but are actually also found beyond those. We are focusing first on expressing the needs for higher resolution imagery and topography, as well as a continued time monitoring of these features. But mostly, this white paper focuses on the importance of correctly interpreting the surface record and understanding the processes that modify the surface of Mars. So knowing, for example, the role of ice, motion, phase changes that drive polygonal terrain, and possibly even the presence of water much after the early Mars period. And this, of course, has implications for surface and climate evolution as well, and as much as for the search for habitable environments and possible finding of resources for human exploration. The status of the paper is in progress. We have a rough first draft, and at this time we're welcoming co-authors and co-signers, from which we expect mostly comments, short written contributions, and brief revisions. If anyone is interested in joining, please contact me. Thank you very much.
Thank you. And Ali Abramson is the last white paper topic for this session, 24.
Cool, thanks. So I'm presenting on a white paper entitled Mid-Latitude Ice on Mars, a Science Target for Planetary Climate Histories and a Resource for Exploration. And our white paper is focused on the outstanding questions regarding the distribution and properties of Mars's mid-latitude ice, especially given its relevance for planetary climate studies and as an accessible resource to enable future human exploration to the planet. In the last decade, there's been a lot of evidence emerging supporting the presence of abundant ground ice in the mid-latitudes of Mars. This includes direct images of new impacts, which expose and excavate ice in the upper meter, neutron spectroscopy, radar reflectors that we think are associated with the base of debris-covered glaciers and ice across some of the northern plains regions as well. Various geomorphologies that are thought to form in ice-rich terrains, and images of scarps like the one shown on this slide, which show about 100 meters of ice. And this was great as like a direct confirmation that there's thick ice in the mid-latitudes, and also that the shallower ice may be a continuous reservoir that's connected to the deeper evidence of ice. And so all of this in the last 10 years has really led to this growing evidence that the ice is relatively pure, extends near to the surface, and reaches lower latitudes than we previously thought. And this potentially provides an accessible record of the recent climate, as well as a large in situ resource for future human exploration to Mars. But we're reaching the limits of the currently available data sets, right as we're sort of on the cusp of unlocking what is here in the mid-latitudes as an ice resource. And the upper 10 meters in particular, which is really important and a dynamic part of the vertical stratigraphy, is still a bit of a mystery just with the gap of the different sensing techniques that we have. And so comprehensive understanding of the nature of this ice would place constraints on Mars's climate history and the total water budget, and the effects of orbital and axial forcing on volatiles, which could open up Mars as a test bed for planetary climate studies, a subject where Mars is particularly important with many similarities to Earth, but without like a biosphere to complicate things, and where orbital and axial forcing dominates climate variability. And the first big step towards addressing these sorts of questions is that we need to characterize where the ice is, how much is there, how shallow is it, and how pure it is. And so we've got a draft in process, and we're happy to add more co-authors, and we would love to start collecting co-signers. And at the one-pager on the METAG website, there's a link to the Google Doc, which I'll also post in the chat, where you can add your name as a co-signatory. So, thank you.
Excellent. Thank you. All right, any other questions for these, please put them into the chat, but right now we're going to switch over to another planetary mission concept study presentation by Wendy Calvin on MORI.
Hey, good morning, can you hear me?
We do hear you. So,
all right, super. So our mission concept, the acronym is MORI, so Mars Orbiter for Resources, Ices, and Environments. If we jump to the next slide, we'll present our team. It was deliberately a very small team. I think those of you who submitted concept studies know that there was not a lot of money involved for the science team. And so this group of people had been working on various aspects of this concept over time, potential discovery mission, but also through the ISAG mission, ISAG report as well. So I want to note here that although MORI and Mosaic were merged because there were some potential similarities, and for budget reasons, these concepts are actually distinct, and we're going to have two separate reports that come out of these two mission concepts. Next slide. So the motivation, I think as you just heard from Ali, there's been tremendous new discoveries in terms of ice and climate and our understanding of nature of where we see buried ground ice. And what we heard from Bryony in terms of we have a more complicated history in terms of diverse and aqueous environments, in terms of both our orbiter and landed assets have shown that we have diverse habitable environments in the first billion years on Mars, but there's major uncertainty in the time and duration nature of these earliest aqueous processes. There's been a bunch of reports going back to NEXAG in terms of looking at both of these, the distribution and origin of ice reservoirs, environmental transitions, as well as looking at the need for water resources and hydrated minerals as potential future resources for future human strategy, future human exploration. The planning for the next decadal CAP report, as well as the midterm review, as well as astrobiology strategies have all re-emphasized this important science. And then the ISAG also looked at an orbiter mission as well. And then as Ali was just saying, from the Mars Subsurface Water Ice Mapping Project, there's a sensing gap between 5 and about 20 meters depth. And so we can actually address this resource need using the same techniques as the science. Next slide. So what we did is we had a series of conference calls to sort out the science trade space, focusing on the different instrument approaches, the radar, spectroscopy, and imaging, which supports them both. We started, in the proposal, we started with actually the NEXAG science questions, but developed a set of more specific science questions and objectives. We looked at the instrument and mission requirements. We had a Team X architecture planning where we actually used existing instruments to kind of scope the costs, because a stated goal was to see, could we get this into a New Frontiers cost box. We had a face-to-face meeting in February where we looked at payload and operation scenarios and mission duration. We had a TeamX mission design the first week of March, which we were able to do in person just before the whole COVID stuff started to blow up. The presentations that were planned to happen before LPSC are now scheduled for May 26th and 27th, and there will probably be some announcements coming out soon about this, and the final reports are due July 28th. Next slide. So we developed for MORI then a science theme based on the evolution of a habitable world with two key questions. The first key question is about the cryosphere, the ice deposits linked to current and recent and ancient climate, particularly focused on distribution and volume of subsurface ice, especially near the surface, vertical and lateral structure of the polar deposits, annual cycling of volatiles between the surface and atmosphere, and the link of ice reservoirs to their formation process and history. The second science theme is how did the crust record the evolution of surface environments and their transition through time, looking at the nature and timing of aqueous deposits, the intervals of the geologic record preserve environments that were conducive to the possible origin and evolution of life, igneous rocks and the record of evolution of magnetic sources, and then modern processes are reshaping the surface. And the bottom in gray are resource-focused theme, fueling the future exploration, and those are again focused on ground ice and hydrated minerals, as well as surface characterization. And we did, although I don't show it here, we did take these objectives and trace them to specific measurement approaches and instrument requirements, and that gives us the next slide, which is our mission payload. Next slide. So we have a complement then of both radar sounding and full polarization PDAN SAR. The goal with the sounder is to get a 0.5 meter vertical resolution in ice, and then the SAR does 100 meter spatial resolution with the potential to do spotlight node and higher resolution mapping. We baselined a color imager that's about 1 meter spatial resolution, but has 20 channels between 0.4 and 1.7 micrometers. We're baselining a next generation shortwave infrared imaging spectrometer, which would get the important spectral region for alteration mineralogy at higher resolution than CRISM, and then also a far infrared emission imager, which would share the telescope with the shortwave imaging spectrometer, but measure 6 to 25 micrometers at better than 100 meter spatial resolution. So we get complementary spectral characterization of both primary and alteration mineralogy. We have a wide-angle camera that would do a daily global map, but has added filters at longer wavelengths, so we can do both water and CO2 ice mapping. And then we have dual stereo cameras that are envisioned to be sort of 5 meter spatial scale for doing stereo, as well as clutter mitigation for the radar systems. Next slide. So we have the TeamX results. I think the thing we had kind of a short fuse to get input into TeamX, and we didn't get a chance to iterate with the radar group at JPL that was doing the study. So what was delivered to the TeamX input was a single band SAR plus sounder instrument concept. So that's where we started with a combined SAR and sounding. We combined the telescopes for the shortwave and the long-wave infrared spectrometers. We only considered solar electric propulsion. Early on, it turned out we could do a standard 93-degree orbit sun synchronous, but then if we could switch to a 90-degree orbit, we could actually do direct sounding over the polar holes that are currently a gap in our knowledge. And the team was actually really excited about that opportunity to do 1 year at 93 and then 1 year at 90 degrees to do the polar sounding. Because we had a stated goal of getting into a New Frontiers cost box, we tried a first D-scope where we took away the higher resolution imager, one of the stereo cameras, but added color to the sort of the 5 meter scale camera. And then the second D-scope was to say, look at ice only with dual band sounding and SAR, and the stereo cameras for clutter mitigation. So those were the three concepts that we were able to push through TeamX. The costs that you see in the box there were given by HQ required cost parameters, which is FY $25 and 50% margin on A to D costs. And so we don't have our detailed TeamX output yet, so I don't have a breakdown based on instrument levels. as well as what are the wrappers for the development and mission level stuff. So the last slide, next slide. So I think from our perspective, Maury takeaways, the best way to approach the global distribution of ice reservoirs is combined sounding plus SAR, but in different bands, different center frequencies, is probably the least risky approach to do this. It appears that multiple science goals are out of the New Frontiers cost box without a significant contribution of either hardware or instrumentation. Single science themes can be strong and credible for New Frontiers, and these themes that we were addressing, 2 of them have been discussed and promoted in many recent reports. And our take on the Mars Ice Mapper as it was presented yesterday is that it could address significant high priority science, but it's, as it's currently envisioned and as it was presented to us, it doesn't look like it's going to do that. So that's it. Thank you.
Great, thank you. I did not see. Do you have questions for Wendy or for any of the other speakers during this session? Please put them into the chat.
So I see Bruce wants me to elaborate on the ice mapper not meeting the science goals. So I'm not a radar person, but my understanding from the radar people is that the band frequency, the L-band frequency that they're proposing for the Canadian radar probably is not going to be able to see through dry overburden. So if ice is greater than a meter or so under dry soil, that's probably not going to have the penetration to be able to see that. I think the other thing that I saw presented yesterday is there's a really narrow latitude band. They were talking about a 15-degree latitude band that was really just focused on what might be probable landing sites. But I think to really understand the ice question, we want to be able to map that lower latitude boundary well, and where that lower latitude boundary is going to be is probably going to be deeper than a meter. So as you go to lower latitudes, ice is going to go deeper to be stable, and they probably won't be able to map those depths.
Thanks, Wendy. Just a clarification question. Michael, I asked if you were doing a white paper and if you were looking for contributors, that this seems a small team. Just make it clear, we included the planetary mission concept studies as context of other inputs that are going into the decadal survey. I'll let Wendy speak to whether or not there's a way for anyone else to contribute toward those efforts or related efforts.
So my understanding, I was not planning to do a white paper specifically on this mission concept because I believe these concepts will be presented to the decadal group. So they'll get the full final report, which will be, I don't know how many hundreds of pages. I think it's 25-page minimum plus appendixes or something like that. So I was not going to do a white paper, but if there's interest, maybe we should discuss whether we need support for a mission concept or signatories that say, yes, this is important science and we want to do it. I mean, in some regard, we have NEXAG and ISAG reports that we can point to, but I'm open to if people think we should have a white paper that promotes this science, or maybe that's actually ALICE plus polar stuff. I'm not sure.
Yeah, I was going to suggest the other area is there a complementary one? So just as Rob referenced a couple of other white paper concepts that are related to the mosaic concept, but they are themselves not the mosaic concept, such as establishing the importance of aerostationary orbiters for doing such science. I think there might be complementary areas that either in collaboration with or completely separate from white papers can go in on these topics. But this was the main point was so that people know what is included in these studies. So if you think something's already covered, then maybe we don't need a white paper. But if you think something's missing, then that's where the white paper idea should come in. Okay, so just Wendy, in reply to your answer to Bruce's original question, she points out it sounds like it may not meet the exploration objectives either. If you would like to elaborate, we have a couple more minutes. Otherwise, I'm waiting to see if other questions come in.
Yeah, I think there's probably some question about whether it could actually answer the exploration goals that they're going for as well. I think that my takeaway was a bunch of stuff that was in the chat box yesterday is that it would be nice if they had a science or a mission definition team that would actually look at what are the goals that they're really trying to accomplish rather than just take a free radar from Canada.
So are there any other comments or questions about the specific white paper ideas that were presented? I did see going by in the chat some comment that perhaps Tim's and mine that were focused on planetary aeolian studies. There was overlap. There definitely is. Tim and I have talked about whether or not they're complementary, and we would cover sufficiently different areas that then we could cross-reference between ours and make it stronger, or if we would want to combine them. I think there's some other areas in here too that follow similar ideas. Leslie Tempari points out, oh, okay. Leslie's just pointing out, Eileen, that Bruce and Wendy's conversation maybe fits into some of the NEPAG finding discussion that XCOM has had.
Yep, understood.
When it comes to processes and climate records, again, the thought to keep in mind, I don't think we'll discuss it now, but for the last part of the discussion for today, again, are there key missing areas? We've heard about aeolian and frost-driven. There were some that focused on comparative planetology, different approaches such as facilities, some mission concepts. We heard a lot about ice science, mid-latitudes, as well as polar. There wasn't as much as I might have expected in terms of mission concepts in these areas. But so those are the things to think about. Are there key ideas that are missing here? Okay.
Serena, why don't we go ahead and go to break then?
Yep, that sounds good. I was just going to point out, Eileen, Tim Titus just gave a comment, Mars as an analog, if that rises to any sort of level of findings. And Michael I brought up okay. We will reconvene at 11:30 a.m. Pacific.